Okay. Chapter 17, we did the geometric model, we've talked about the binomial model, and today we're going to keep talking about the binomial model. You need to make sure that you're using some sort of notation in your homework or something if you're using your calculator. Because on a free response question, if you just put a number down, no one's going to be happy. If you just put a number down and you just happen to miscalculate it because you typed one wrong number in your calculator, you get 0 credit. However, if you wrote down what you were doing, then you would get at least partial credit, if not full credit, if you have everything written out correctly and ready to go. So if you're doing geometric model or the binomial model, you need to identify that you're using it. Okay? So if you're using the binomial model, you would need to make sure that you wrote down that you're using the binomial model with n number of trials and p the probability of success. At the very least, that identifies what you're talking about. Right? X is already defined for you, your random variable. It's the number of successes in n trials. So I will try to model some of that notation today when we do some things to make sure that you're practicing it. You should be able to find the probability, binomial probability for any of the questions we did on Friday. Again, we're looking for a number of successes and a specific number of trials. And there is 2 calculator functions for that, binomial PDF and CDF. PDF helps you find exact numbers, and CDF helps you find cumulative values. And then you have the mean and standard deviation for this model, which are also on the AP formula sheet. But if it asks you for the mean or standard deviation, you should be able to calculate it. We're going to have to do a lot of those today. Okay? Now, here's the issue. This is an example from the book. I screenshotted some information. Suppose the Tennessee Red Cross anticipates the need for at least 1,850 units of O-negative blood this year. It estimates that it will collect blood from 32,000 donors. How great is the risk that the Tennessee Red Cross will fall short of meeting its need? We've just learned how to calculate such probabilities. We can use the binomial model with n equals 32,000 and p equals 0.06. So I think earlier in the setup they identified type O as 6%. All right? You have Bernoulli trials because you're looking at O negative or not. You have a probability of O negative, so the probability for not, and you assume that each donor walking through the door is independent of the next. All right? So if you're going to calculate a probability, it would be binomial because you're looking for a specific number of successes and a specific number of trials. So if you're looking for the probability of getting exactly 1,850 units of O-negative blood from the 32,000 donors, this is the formula you would use, or you would use binomial PDF, right? You'd have 1,850 successes out of 32,000 trials. The probability of 0.06 is your probability of success. You could calculate that. However, the calculator that we have are going to end up estimating probably. It might not be the best exact probability because you have to find that number of combinations in the front of your formula, right? And the number of combinations when you have 32,000 trials is rather excessive. And so your calculator is going to eventually give up and it's just going to estimate. Okay? It'll do it. It'll give you a probability. I'm just saying I can't guarantee it's going to be exactly what it's supposed to be because the number of combinations is so large. All right? Does that make sense? Then it said, really, we're looking to make sure we got at least 1,850 units. That means we want 1,850 units or more. So really, you're using CDF. You're trying to do a cumulative amount, right? So then you're just going to be adding in more combinations. So it just becomes, your calculator is going to give you an answer, but it's going to probably be rounded somewhere at some point because the calculator's going to give up trying to find that specific number of combinations. All right, it's just a little bit. Okay? So when you have a large number of trials, so not when you're dealing with, like on the homework, with all of the arrows questions. She was shooting a specific number of arrows, and it wasn't very many arrows. It was like 6, right? So that's not a large number, whatever. But when you're dealing with a large number of trials, because that calculation can be a little tedious for your calculator, you could also approximate the probability using a normal model. All right? After Christmas, you don't know this is coming, but I do. After Christmas, we're going to be using normal models all the time. All right. We use normal models in chapter 16, so we recently talked about them. I know we hadn't talked about them since chapter 6, but we talked about them in the last chapter. So I need you to start getting more comfortable with the normal model. All right, so this is a great instance, again, where it comes up. A lot of things in this class end up going back to, can I use the normal model to do this? So you need to be comfortable with it. So if there's a large number of trials, we can find the mean and standard deviation of the scenario using our binomial distribution, n times p and the square root of n times p times q. All right. And as we have those, we can approximate the probability using a normal calculation. All right. So we're using the idea of binomial by finding the mean and standard deviation, and then we go through and we use the normal model to find a probability, to make an estimate. All right. So if we were trying to figure out, again, they want at least 1,850 units of O negative blood. I could draw the model. It tells us n times p is 1,920, and the standard deviation is 42.5. So I could draw this out. The mean is 1920. I could add in standard deviations of 42.5. And I could keep adding and subtracting them. Do 1, 2, and 3 standard deviations above and below the mean. Yeah. And if I was looking for at least 1,850 units of blood, this is the mean units of blood is 1920, then I'm looking for somewhere down here and up would be the probability of getting at least 1,850 units of O negative blood, right? Normal calculations allow you to put in a boundary. That's what you guys don't like about the binomial calculation, is that you have to decide when it says at least or some about how many, and then if I'm subtracting from one or I'm not subtracting from one, and am I using CDF and all that stuff. Normal probabilities allow you to put in boundaries. I want to go from this number to this number with this mean and this standard deviation, right? It's rather straightforward. Okay? So that's why I think that maybe you'll be more comfortable with that. Maybe you won't be, and you want to use the binomial model, and that's fine. Okay? But so I would just be able to go into normal CDF and I went from 1,850 units of blood to quote-unquote infinity units of blood, right? With a mean of 1,920 and a standard deviation of 42.5. Does that make sense? I could calculate that using normal CDF. Again, your calculator will do it for you with a binomial probability as well. It's not wrong. Okay? Both of them are going to be estimates, though. So the idea today is we can use the normal model to do what we were doing if we have a large sample size. So I'll do some examples here in a second. Now there's one thing. How do you know if your sample size is large enough? 32,000 is large, I get it. All right, but is 500 large? Is 700 large? It's going to depend on the probability of success. So if you're going to use a normal model, you will always have to justify using it by saying that your sample size is large enough. And in order to prove that it is large enough, you always follow this condition. And we call it the success-failure condition. And it just says that your number of possible successes and your number of possible failures, or expected successes, are both greater than or equal to 10. So you need to do n times p and n times q and make sure they're both greater than or equal to 10. And if they are, your sample size is large enough to use the normal model. If they're not, you need to use the binomial one because it's not large enough. Does that make sense? It will ask you, in the first questions I give you tonight, it'll ask you to justify it, so you'll have to get in the habit of doing it. On other questions, when it's not asking you specifically about the normal model and you just decide to use it, you will have to justify it yourself. If you don't justify it, then you're going to get yourself into trouble because maybe you can't always use it. Okay? This is why this is important. After Christmas, when we're talking about all sorts of other things, there is always, and I mean every single time, a set of conditions that must be met before you can do the question. You have to check the conditions in writing on paper before you can do the rest of the question. All right, it's going to be part of the AP rubric for every single question I'm going to ask you about after Christmas. So in the habit now, you should be checking just this one condition to use the normal model. So just go ahead and start practicing. Technically, if you look at my homework, I haven't been forcing the issue, but if you're going to use the geometric or binomial model, you should check that you should have Bernoulli trials. So if you look at my homework, it says, probably at the very beginning, it says 2 outcomes, probability of success, independence, right? You need to be checking those things. All right, I'm going to do some examples. The first two, we might do the third one, I don't know. The first one is just what you did on Friday. So it's going to be practice. I'm going to have you do it. And then we're going to use that scenario to build up to what we did today in class. All right, that way we can review inside what we're doing today. Because I know some of you guys had questions from Friday. So it says a certain tennis player makes a successful first serve 70% of the time. Assume that each serve is independent of the others. If she serves 6 times, what's the probability she gets? And there's 4 questions. So we do have Bernoulli trials because we have 2 outcomes. We have a successful first serve or an unsuccessful first serve. It says that each serve is independent of each other, and we know the probability of getting a successful first serve is 0.7. All right. I want you to go ahead and practice these 4. Write them down in your calculator, whatever you need to do. And then I have it under the shade over here. I have all the right answers with appropriate notation if you wanted to practice that. All right, here are the answers. So, for A, again, I'm using appropriate notation because I didn't do that when I taught this, so I want to make sure I do that now. You identify what model you're using. All of these, you know, have the same model. It's all binomial with 6 trials and a probability of success of 0.7. I then also show what probability I'm trying to find. So for A, the probability she gets all 6 serves in, that's the probability that she gets exactly 6. So you would need to use binomial PDF in your calculator and use 6 trials with exactly 6 successes. So you get 0.118. Questions about A? That would work on that one specific. Yeah. On B, exactly 4 serves in. That's 4 out of 6. So we're looking for the probability that x equals 4. So again, binomial PDF, that's an exact number. So exactly 4 successes out of 6 is 0.324. Questions on B? Yes. C, at least 4 serves in. At least 4 means you want 4 serves in, or 5 serves in, or 6 serves in out of 6. So you want to use CDF. C stands for cumulative. But CDF starts at 0, and you can't make it not start at 0. So it's going to start adding from 0. So if I use CDF, it's going to start going 0, and then 1, and then 2, and then 3, etc., etc. So because it says at least 4 serves in, I want to know the probability that x is greater than or equal to 4. So I'll need to do 1 minus binom CDF all the way up to 3. That makes sense. So I'll add together 0, 1, 2, and 3 and subtract that out. So you get 0.744. Questions about that? Then on D, it says no more than 4 serves in. That's x less than or equal to 4. So that's 0 serves, or 1, or 2, or 3, or 4. That's what CDF does. CDF calculates from 0 and goes up. So you're using binomial CDF, calculating up to 4 successes. And you get 0.58. Questions about 25? As a good review of what you were supposed to do on Friday. All right. Now, using the same scenario. That's why I did 25, so we know what's happening in 27. On 27, suppose the tennis player in exercise 25 serves 80 times in a match. What are the mean and standard deviation of the number of good first serves expected? Since we're using a binomial model, what's the mean? How do I find it? Number of trials times the probability of success. So in this case, 80 trials times 0.7, and if memory serves me correctly from this morning, that's 56. Right, so we expect 56 good first serves out of 80. N is the number of trials. This is a mu as in mean. Then the standard deviation, how do we find that? Perfect. If you don't like Q, that's fine. So if you don't like Q, on the formula sheet it doesn't use Q because Q is in standard notation. That's what our book uses. So on the formula sheet, it has the square root of N times P times 1 minus P, which is what Q is. So it spells it out for you on the formula sheet. All right. So if we're going to calculate that here, we have the square root of 80 times 0.7 times 0.3. It's just the complement of whatever P is. And if I remember that correctly from this morning, it's 4.1. People are checking this for me, I'm hoping. So, excellent. All right, so we can answer A. Not a big deal. B, verify that you can use a normal model to approximate the distribution of the number of good first serves. So in this case, it's leading you through it. So it says verify that you can. If I'm going to verify that you can, what's the one condition I have to check to see if I can use a normal model or not? The success failure condition. I need to double check that the number of expected successes and number of expected failures are both greater than or equal to 10. So you have to write it out. It's not something you just do in your head and say, okay, that's great. You need to actually write it out. So N is 80 times 0.7. You already did that. That's the mean. So 56 is greater than or equal to 10. You can calculate the number of expected failures by doing 80 times 0.3, but if you have 56 successes in 80, then how many failures should there be? Which is 24. Again, that's also greater than or equal to 10. You can also calculate it. You can still do 80 times 0.3. It does the same thing. Okay? So they're both greater than or equal to 10. So because we have enough successes and enough failures expected, we could use the normal model. Totally fine. We would use the normal model with a mean of 56 and a standard deviation of 4.1. Because that's what we had in part A. We use the binomial mean and standard deviation as the mean and standard deviation of the normal model we're going to use to estimate. Everyone with me? Questions so far? That is what has been defined for us. Always 10. All right. C says use the 68, 95, 99.7 rule to describe this distribution. When it says that, it just means draw the picture and label it. If you like drawing them, then you're my best friend because that means you're going to do what you're supposed to do on every test. Because no one else listens to me and they don't draw them and they don't get the points they need on the free response questions because they just didn't draw a picture that took 5 seconds to draw. Okay, so the mean was 56 and the standard deviation was 4.1, so that's 60.1 and 64.2 and 68.3, okay? And then 51.9, 7.8, and 43.7, maybe? Okay, excellent. All right, so then we need to say that this is the number of good first serves. That's what we're talking about. Those numbers represent. And then we're supposed to label it using 68, 95, 99.7. I realize that my bell curve could have been way better. But at least we got the idea. $68, $95, $99.7. I have done what it's asked. I have created it, labeled it. Everyone happy with part C? On part D, what's the probability she makes at least 65 first serves. We want to know the probability that she makes at least 65. All right, there are two ways to do this. One way is to use the normal model because we have been talking about this entire question. So I'm going to assume that they want you to. We already have the model in part C. Right, so you can use your model. We want at least 65. 65 is in here somewhere. At least 65 means 65 and up, right? So that's the section I would want to find the probability for. So in your calculator, how do you calculate that section, that probability? What function do you use in your calculator? Normal CDF, right? Because normal CDF allows us to put in boundaries. So we'd have our lower boundary would be 65, upper would be, again, infinity, but not really. And then we would have a mean of 56 and a standard deviation of 4.1. .014. Okay. So that is one way to get that answer. That would be acceptable. I would use the picture. This is what the problem is. The AP exam, they are going to give you like no credit for writing that out. That's going to get you nowhere. So if you draw the picture and you shade in, you have the lower and the upper boundaries, and you have the mean, and you have a standard deviation shown. And so you don't have to worry about what you're supposed to write because you do the picture and they take that. And they're like, okay, they know what they're doing. All right. If you write this down, most of the time they won't give you credit. If you label it, so see I labeled it up here. If you label it, they might give you credit for it. Because then at least you know what the numbers were. Maybe. I'm sorry. All right, so question with a normal approximation. Second way to do this. Is 80 a lot? Not really. So maybe if they didn't talk you through all this other stuff, like if they didn't do B and they didn't do C, and they just said what's the mean and standard deviation and what's the probability, then maybe you didn't think to use the normal model because it's only 80 serves. Like that's not extensive. All right. So you could also use the binomial model. You don't have to approximate it. Okay? So with the binomial model, still doing at least 65. If we're doing at least 65, that means we went 65 and greater, so we'd have to do 1 minus, right? We'd have to do 1 minus binom CDF. We have 80 trials, a probability of success of 0.7, and I want at least 65, so I need to subtract out 0 to what? 64, right? If you do this one, I think you get 0.016, just from this morning. Right, they're both not going to be the same. They don't give you the same probability. Right? The binomial gives you the binomial probability that it calculates in the calculator based off of your formula with the combinations, etc. The normal model is just approximating the probability based on the mean and standard deviation you provided. Okay? So they're not going to be the same. They should be close, though. They were close. Doesn't matter. Right. Yes. So that's why if this is a free response question, doesn't matter. In a free response question, if they aren't setting it up in a specific way, you could have done it both of these ways. Like if they didn't give you again to like make the picture and they weren't leading you through it, which they're not going to. You could have answered it either way. So if you had to write out your work, you would need to draw the picture and like shade in and find a probability for the normal model, or you would need to write out that you're using the binomial model with a mean and standard deviation of blah 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 with 80 trials so that you could calculate the probability. So you would need to use this notation. Just showing that what model you're using and so that they knew what you were doing. Both of those are the correct answer. So when you check your homework today, if you check your homework today, you will see that on my answers, there are maybe 2 answers. I had both of them because it's not wrong. So you have the normal answer, you have the binomial answer. You don't have both, you have to have one of them. Okay? Questions about this? To some people, you might be more comfortable with the normal model already, and so you just want to do those, and that's fine. I think it's easier to calculate because you can put in boundaries. If you don't want to do that, you can use the binomial model, and that's fine. No big deal. Whatever you want to do. Just make sure you check everything first. So if you were going to do this question with normal, you have to check success, failure. You need to draw a picture probably or something so you can calculate the probability. All right? Questions for me? Do you want to do any more examples, or are you good? Okay. This is your homework down here. Yeah. Yeah, when you're using normal models, you always use CDF in your calculator. We never use PDF because it doesn't really do anything we need it to do. With geometric and binomial, PDF do specific things for it.